Okay. So we were discussing Banach algebras. Okay. So here be a Banach algebra. I should have done this last class. Let me do it here. Banach algebra. And you have an element A. Then we defined spectrum, resolvent, and we defined a resolvent function. Okay, sigma x is the spectrum. All those lambda in C such that x minus lambda is not invertible. U of x equal to all those lambda in C such that x minus lambda is invertible. Okay. Then we define this function, R function, which is Rx or what is it? It's this is my R function from Rx. No, this is I think right. Rx is a function from Ox. This is a subset of C to A, which is given by lambda going to lambda or mu going to x minus lambda inverse. Okay. Now we want to prove the following proposition, which is what is called spectral radius formula. So before I want to define what is spectral radius. So for x in A, x in the Banach algebra, Rx, which is the radius, spectral radius equal to supremum of lambda in lambda such that lambda in sigma. It is just the supremum of lambda in sigma. So maybe I need a mod lambda. Yeah. Okay. Supremum mod lambda. Okay. So spectral radius formula. So this says the following: if x is an element of A, then this gives a formula for this spectral radius R of x, which is equal to limit. This limit exists, and it is this limit norm x power n whole power 1 by n. So this limit exists. So this is the spectral radius formula. Once this is proven, then the corollary to this. So maybe I'll come back to the corollary later. Okay. Proof. Okay. So we have already proved in the last class that if we have a phi in A star, a linear functional, then the function lambda going to phi of Rx lambda. This function is analytic on rho x. We proved this. Okay. So this function is analytic on this, okay, on rho x. So that's what we proved. Further, we proved that x minus lambda inverse, which is what is Rx is, okay, equal to, we proved this formula, n equal to 0 to infinity x power n by lambda power n plus 1. Okay, if I apply phi here, okay, yeah, phi here, then this just becomes, phi is continuous and linear, and you can insert the phi inside. Okay. So this phi of x power n is a number, okay, which does not depend on lambda. So the function is lambda going to this. So this is the Lorentz series expansion. Expansion of this function phi of Rx, okay, on this lambda such that mod lambda greater than norm x on this region. Okay, we proved that if mod lambda is greater than norm x, then x minus lambda is invertible and the inverse is precisely given by this. This is what we prove. So this when mod lambda is greater than norm x, then x minus lambda inverse is given by that, and phi of x minus lambda inverse is given by this series. So this is a Lorentz series which is valid in mod lambda greater than norm x. But you know that if we have a Lorentz series, see which is there is no. If we have a Lorentz series which is true in this, or can be infinity also, then the Lorentz series is unique. Okay, but if it is infinity, you have to verify that the limit exists in the infinity. But since I hope all of you done some complex analysis, see, this is well known, no? Okay, if not, you just go and read something about Lorentz series in any book. Okay, it's very simple. Okay. Since limit mod lambda goes to infinity, phi of Rx lambda, okay, mod of this equal to 0. Okay, so the limit exists at infinity. The Lorentz series is valid. The above Lorentz series, the star is valid in whole of rho x. Okay. This is valid in that. Maybe you can even just say this. You can say that all mod lambda in this region. Lambda such that mod lambda greater than or x. This makes sense. This is because we already have that Lorentz series, and then the limit exists at infinity. Because of that, this is true. Okay. Okay. So in particular, what we have is this is right. So this implies for all lambda greater than Rx, okay, we have that. What do we have? We have this sum. This series exists. In particular, we have that phi of x power n, lambda power n. This goes to 0 in particular. That is phi of x power n is less than or equal to k times lambda power n for some k. In particular, it's bounded for some k, right? That's a series which converges. So the elements has to go to 0. In particular, this has to, there is a lambda power n plus 1. That doesn't matter. You can take it lambda n. And then it is bounded. Since this is true for all phi, this means it is weakly bounded. We have already seen that if weakly bounded implies actually it's bounded. Or you use uniform bounded expression. That's what being used. That's what is used to prove weakly bounded implies this is true for all phi. For all phi in A star. This is true by uniform boundedness principle. X power n, this norm x power n is less than or equal to k times mod lambda. You can take 1 power k there. So this implies x power n whole power 1 by n is less than or equal to k power n mod lambda. Okay. Now you take n going to infinity and mod lambda going to Rx. Not n power n going to infinity. You want to take the lim sup. Okay, but I don't take limit may not exist. So I take the lim sup here. Lim sup. That implies lim sup x power n 1 by n. Lim sup is less than or equal to k power 1 by n goes to 1. And lambda is there, and lambda is, this is true for all lambda greater than this spectral radius. So this is okay. Is fine. This is okay. See, we just use the analyticity to prove that there is a series, and then for all lambda, that thing converges to 0. So it is bounded by uniform boundedness principle. This norm x power n is less than k times mod lambda power n. Then I take the lim sup here. Okay, I mean you can take the limit here. You can take the lim sup on the left hand side, and this implies lim sup of this x power n whole power 1 by n is less than or equal to mod lambda for all lambda greater than Rx. So in particular, it is smaller than or equal to Rx, right? Okay. I hope it's okay. Okay. On the other hand, we want to prove the lim inf. On the other hand, we want to talk about so see, we have spectral mapping theorem. Assume that we have proved, okay, by spectral mapping theorem. So by spectral mapping theorem, we have that. I mean, we have P of sigma x is same as sigma of P of x. In particular, it's true for x power n, the polynomial x power n. And in particular, it's true for the spectral radius, R of x power n equal to R of x power n, right? This is true. So this implies R of x equal to R of x power n whole power 1 by n. Okay? But then this is less than or equal. We have already proved that notice notice that for all lambda in sigma of x, mod lambda is less than or equal to norm x. Because if mod lambda is less than greater than norm x, then the x minus lambda is invertible. We have proved that. So because of that, mod lambda is less than or equal to norm x. So this is less than or equal to norm x power n whole power 1 by n. Okay, this is true for all n. So this implies R of x is less than or equal to lim inf x power n whole power 1. Okay, so that's what we want to prove. This is R of x is smaller than the lim inf, greater than the lim sup. Okay, so they are all equal and the limit exists. Okay, so this is what we want to do. I hope this is fine. Is okay?
Yeah.
Okay. So now suppose t is normal. T is a function which is, let's assume t is b of h. So now let us come to our Banach algebra b of h. You can ask, you can talk about normal elements in the cis Banach algebra itself, but that's not our aim. We don't want to study Banach algebras or cis algebras. We just want to use those techniques to study operators. Okay, suppose t is in b of h and t is normal. T is normal. Okay, then sigma of R of t. The spectral radius. T is a Banach algebra element, so sigma of t exists. Sigma of t makes sense, and you can talk about the spectral radius of t, R of t. So R of t equal to norm x. If it is normal, norm t. Okay, proof. I think we proved this for normal t, norm t power 2 power n equal to norm t power 2 power. We proved this, no? Did we prove this last class?
Yes, sir.
Yeah, not last class, the previous class. Yeah, we proved this. So this implies t power 2 power n whole power 1 by 2 power n goes to equal to norm t, right? A subsequence which goes to norm t. We know that limit exists for this equal to norm t. So this implies t power n whole power 1 by n will converge to norm t. Because there is a constant subsequence that has to converge, so it goes to norm t. So this implies R of t equal to norm t. Okay. So for normal elements, the spectral radius is same as the norm of t. Okay. Okay. So norm t is either norm t is there or norm minus norm. It's not precisely that. It says that R of t equal to norm t. Okay. That's all. there exists a lambda such that mod lambda equal to R of t. It's compact, so the supremum should exist in that. So there exists a lambda such that mod lambda equal to norm t. Lambda in the spectrum such that mod lambda equal to norm t. Okay, so that's what. So what is next? So now I want to prove something for self-adjoint elements. Okay. So you know what is self-adjoint. If x equal to x star, that is what is called self-adjoint element. Okay, proposition. Let P be a polynomial. Okay. Then x is self-adjoint element, x equal to x star. Then norm of P of x equal to, this is looks like this is P. P of x equal to, P is a function. Okay, so it is a function on sigma of x. So which is equal to P of t mod P of t, t in sigma of x. It is just a supremum norm. It's a function on sigma of x. It is just a supremum norm of this P that is equal to P of x. You can notice that this is true for x. If x is normal, okay, then the norm of x is same as the identity function. I mean, x going to x. That function, it's norm of that, right? I mean, if you take the function, if you have take p equal to x itself, I mean p equal to t itself, for example, x may be confusing. This polynomial, p equal to t, okay, this monomial you take, then p of any normal element t is just t itself, right? So then norm sigma, I mean then this norm of that p is nothing but the spectral radius of t, right? And that is same as norm t. That's what we have proved for normal elements. Okay. Here we are proving, we are saying that for a, I mean, what I'm saying is whatever I have written is true for normal elements in general. But here I'm saying it for a self-adjoint element. It is true for normal element also. We'll see it later. But here the proof is simple for self-adjoint element, and that's what we have proved. Okay. I mean, in a Banach algebra, we don't have the concept of star and all. We want to use what we have proved for Banach algebra and the spectral mapping theorem, which we have proved for Banach algebra, and we want to use it here. Okay. So by spectral radius formula, it is true that norm t is same as spectral radius. Which that spectral radius is nothing but supremum of lambda, which is, I mean, if you take the identity polynomial p of t equal to t, not p of t equal to 1, not that identity, p of t equal to t, that polynomial, then this is true for any normal element with that p. Okay, here I'm saying if you take any polynomial p and if you take any self-adjoint element x, then norm of p of x is just the norm of the polynomial. Okay. Okay. So the proof is easy. So x is self-adjoint. So p of x is a polynomial with, I mean, it can have complex coefficients, but x is self-adjoint. So p of x star is nothing but x is self-adjoint. So if you take the, I mean, when you have a polynomial in x, I mean, what is p of x? P of x, you have a polynomial. Instead of the variable x, you are going to substitute this capital X, this operator capital X. Okay. Then if you take the star, then all the coefficients will become bar, and then the x power n will become x star power n, right? That's what will happen. But still, since x is self-adjoint, this is just you take the polynomial with the coefficient, you take the conjugate of the complex coefficient. It is just p bar x, right? This is true. P of x star is nothing but p bar x. Okay, it's just the bar of the polynomial. Just take the bar in the coefficients. Okay, conjugate in the coefficients. Okay. So now p. So what is now we want to talk about this p of x square, which is equal to p of x star p of x, which we have proved for any t, norm t square equal to norm t star t, which we have proved earlier. Okay, this is equal to that, which is equal to p bar. Okay, which is mod p square, whatever mod p square is, mod p square x, right? This polynomial. But what is mod p square? Mod p square, notice mod p square is a polynomial with real coefficients, right? If you have p of x and if you have p bar x, and you take the product, then the x power n will be summation. It will look like this: ak a n minus k bar, and if but then ak and n minus k bar will interchange, and you will get only the real part of that. You will get only real part. Okay, is that clear? If you have a complex polynomial, you take its bar, then mod p square will have only real coefficients. Okay, check. So this is equal to, why do I need real coefficient? Because why do I need real coefficient? Because that is just the, because that's also normal. I want to use that. That is self-adjoint, so it's also normal. So p square x is self-adjoint, right? In particular, it's normal. Okay? In particular, norm p square x is self-adjoint. Okay? So I can use the spectral radius formula. Spectral radius formula says that this is same as equal to p mod p square t, right? Mod yeah, norm of this equal to the spectral radius of that, or of mod p square x, right? This norm is same as this by the spectral radius form, correct? Okay. And this is nothing but mod lambda, lambda in mod p square, I mean sigma of mod p square. Okay. But this is equal to, this is same as by spectral mapping theorem. This is same as, so this is spectral radius formula, this is by spectral mapping theorem. This is same as, you take.
Like it should be a number, not a set.
Yeah, sure, supremum. Okay. This is same as supremum of p of lambda, mod p of lambda, lambda in mod p square, and you just take lambda, mod p square of sigma. No. It is just the supremum of lambda for lambda in that, and which is same as p square of sigma of that. I'm just following one step, okay? With p of lambda, lambda in. Let me explain. Lambda is sigma of t. I mean, this is the supremum of lambda. Here also supremum. Okay. Supremum of mod lambda such that lambda is in sigma of that, but that is same as lambda in mod p square of sigma, which is equal to right. This is same as mod p square of sigma lambda such that this is equal to that. Then that is equal to mod p square lambda. P square lambda. Okay, that is equal to norm p square with something sigma. Okay, sigma. But then that is same as I mean, that is same. Mod p. I mean, this is same as mod. I mean, p square is all mod p square is a polynomial, but that the norm is same as mod p sigma mod p whole square. These two are same because you are just taking the supremum over square, and these two are same. That is clear. Okay, so from here we started with p of x square. So this implies p of x norm of this is same as. You don't need mod p here.
So from the spectral mapping theorem, it follows directly that R of mod p square x is mod p square of Rx.
R of
Right.
mod p square x is
Mod p square of
that's
Rx.
right. That's right. Yeah, that's what I have written it again. Yeah, that's okay. Yeah.
Okay. Yeah.
Yeah. Okay. So this implies mod px equal to px. Okay. This is same as norm of this. Okay. Mod p square is a polynomial, and I want to take its norm over this. Okay. Okay. And that is same as mod p square sigma mod p square. Both is, this is like C star identity for the sigma C of sigma t. Okay, that's there also sigma. This it's true for any polynomial. This is true. Norm of f. Norm of f square equal to f bar f. This is the star of that. You can take this. It's norm. Okay, this is true. You can directly check. Okay, so that's what I'm using there. Okay, so this is true. Is that fine? Is this okay?
Yes.
Okay. Okay. So if you have a problem, you stop me. Anyway, this is in the book. It's direct. Okay, for self-adjoint, what's it? Okay, for self-adjoint element, this is true. Now we want to look at what is called a Cartesian decomposition and prove something about something for the normal operators. Okay. These normal operators are like complex numbers. Okay, so that's what this says. So this is proposition. And I hope all of you know this. This is true for any matrix. Z is any operator. T is any operator. Z is any operator. Then there exists xy self-adjoint such that Z equal to x plus iy. Unique. Okay. That is just clear because then x is just Z plus Z star by 2. Y equal to Z minus Z star by 2i. Okay, so they are self-adjoint and it has to look like that. It cannot be anything else. Okay, so this you must be knowing from matrices, and that is true for any operators also. Okay, so this is what we call as the Cartesian decomposition for any operator Z. So now we want to prove the following: that Z is normal. Let Z be normal. Okay, and Z equal to x plus iy. Okay, with xy self-adjoint. No, I'm not saying about self-adjointness. I want to prove something for now. Let Z be an operator. Okay. B of h. Okay. Then let Z equal to x plus iy with xy self-adjoint. Then the following are equal. 1, Z is normal. Okay. 2, that is equivalent to saying norm Zx square. Zx square equal to xx square plus norm yx square for all x in h. Okay. Then the third condition is X and Y commute. Okay. So this is, I mean, if you have, this is the decomposition of Z into two self-adjoint element. This is like if you have any complex, if you have any complex number, then you can write it as alpha plus I beta. So it's like it's like that. Okay. Proof. One second, I'll just come in a second. One second, I'll just. Oops. I have to connect again. Okay. Okay. Sorry. Okay. So what was I doing? Yeah. These are good. As it is normal, then this is true. Okay. So what do you have? We want to talk about norm Zx squared equal to, just write the definition, Ax square, but then that is equal to xx square plus I will go away. So Ax square plus 2 real part of x xx I yx. Now you can take this I out as minus I. Okay. On the other hand, norm Zx square is also equal to Z star x square. We proved it for any normal operator. Norm Tx equal to norm T. Norm Tx equal to norm T star x. I mean, for any operator, norm T and norm T star are same, but that's supreme one. But for each particular x, norm Tx equal to norm T star x. We proved it for a normal operator in the two class before. Okay, so because of that, this is equal to, this is just xx. What is the star? Is just the conjugate. I mean, just like taking conjugates. So that is equal to xx square, ax square. So there is a minus here. 2 real. There is a minus here. Minus iyx, and that will come out. So which is jix, xx, ax. Okay. There will be a minus I. Minus I will come out as I. Okay, from the inner product. So these two things imply. So Z is normal. I mean, this. Let me not even write this. So I have just made this computation. So Z is normal is equivalent to saying real part of I xx yx equals 0. So 1 is equivalent to 2. Okay, this is equivalent to that. X is normal means is equivalent. So this is an equivalent condition. Did I prove the equivalent condition? If Zx equal to this. Did I prove the equivalent condition? That anyway, let's just do it. See, if you have any, I mean, this is just a digression. Did I prove it? I want to say that T is normal.
Yeah, you did it.
Yeah, equivalent to saying T norm T Tx equal to norm T star x. It's one way I proved. The other way also did I prove?
Oh, so the converse you didn't prove that norm of
Yeah,
Tx equal to
so
norm T
let's
star
do
x
that.
is there.
Let's do both of
Okay.
them. Okay. So T is normal. So T star T equal to T star. Okay. In particular, T star T x x equal to T star x x. Do you know that these two are equivalent? Did I say this in the last course? So I will say this now. Okay, after this I will come back to that. Okay, I will. So here I have to do this. Let me first let us do this digression and then come back here. Two things I want to prove. T is normal is equivalent to this. This I want to prove. T is normal means T star T equal to T star. So that is equivalent to saying. So this will follow if you two operators if Sxx equal to Txx, then S equal to T. This is by polarity, the what is called polarization identity. It's fine because the polarization identity says that you take this bxy equal to sxy. Sorry, sx. Okay, sxy. Then 4xy, 4sxy. I mean equal to summation I power k s x plus iy x plus iy I power ky I power ky. Okay. So if sx x equal to this is for all x, then we imply sx equal to 0. So if sxx equal to txx, then that implies by polarization identity, it follows that sxy equal to txy. So this implies, but this is true for all x and y. This implies s equal to t. Shall I go one by one? Okay, let me come back to the proof of this later. First, I want to prove these two statements. Okay. So the first statement is if t is normal, then I want to prove that tx norm tx equal to norm t star x. These two are same. Let me one by one. I will come back. First statement I want to prove is if sxx equal to txx, the inner product between sx and x and tx and x is same for all x, then s equal to t. Okay, this is the first thing I want to prove. Okay, so to prove this, it is enough to prove that sxy equal to txy. Okay, because then it means that the linear functional. I mean, because the linear functionals on the Hilbert space is given by inner product. This is true for all. This means this is s equal to 2. This we have seen already. Okay. This is because the linear functional separates points in a Hilbert space, in any Banach space. And here the linear functionals are given by the inner product. So because of that, then Sx equal to Tx for all x, that means S equal to T. Okay. So that, but then that follows if Sxx equal to Txx. This is what is called a quadratic form. Okay. But then then that will imply Sxy equal to, I mean, you can expand it by the polarization identity. But x plus I power ky is another x. Okay, so that those inner products are same. So that implies sxy equal to that is same. So it follows by polarization identity. If this is true, then then s equal to t. Okay, that's fine. So to prove that t star t equal to t star, this implies this is equivalent to saying one way is true, t star xx equal to t star xx. But the other way is also true from whatever the discussion we have done. Okay. So now this is equivalent to saying that if you expand that, that is equal to norm you can take the tx on the other side, tx square equal to, you can take the t star on the other side, t star. Okay. So whatever I have made the digression here, that implies this. Now we have proved the other way also. So these things implies that now we come to this proof of this proposition. The proof of the proposition says that if z is equal to x plus iy, then z is normal, then norm zx square equal to corresponding xx square plus yx square. It is just like computing the mod. How you compute the mod in complex number, that's what is true. So it is, z is like a complex number. Okay, in this property. Okay, norm zx square equal to, you compute norm zx square, you compute this xx square plus iyx square plus 2 times real part of something, and you get for the star I get the real minus of the real part of something. Since for normal element zx square it is normal, it is equivalent to saying zx norm zx square equal to norm z square x square. So these two, the real part whatever we have the extra term, that has to vanish. That is the equivalent condition for being normal. Okay, so that implies that vanishes. Okay, so this implies 1 is equivalent to 2. This is says 1 is equivalent to 2. Okay, the whatever the remaining part we have, that vanishes. 1 is equivalent to 2. That is what is 2 is. Okay, norm zx square equal to norm x square plus norm yx square. I want to prove the third condition. It is equivalent to the third condition. Okay, to prove the third condition, so now we know that 1 is equivalent to 2 and 2 is equivalent to saying that real part of I xx yx equal to 0 is equivalent to saying this is equivalent to saying xx yx is real. Okay, since x is y is self-adjoint, this is saying yx xx is real. Okay, this means this is equivalent to saying, let me come back to this. This is equivalent to saying yx is self-adjoint. Okay, I will come to this. If yx self-adjoint, then that is real, but I am saying this is true the other way also. Yx is self-adjoint, but y is self-adjoint is same as saying yx equal to yx star, which is equal to xy. Okay, so I have to prove this statement. This statement I have to prove. Everything else is fine. Is this fine? Did I go fast or something? But it's all very simple things. I'm saying that we have 3 conditions. The first condition is equivalent to second condition we have proved. Now we want to prove the first 2 conditions are equivalent to the third condition, which is equal to xy equal to yx. We expanded this norm zx square like this, and then we have some cross term, real part of something. So 1 is equivalent to 2 is same as saying the whatever the cross term, that is equal to 0. Then I'm saying that the cross term equivalent to saying equivalent to 0 is same as this inner product is real. That's what this means. Real part of something is 0. Real part of I times something is 0. Then the whatever the I times something, that has to be purely real, right? Right?
Yes, sir.
Right. So that's what I'm saying. Then that is purely real is saying that that is self-adjoint, and that is what we have proved. So now I have to prove the following. This I should have done the last class proposition. If we have a t is in b of h, if txx is real, okay, then t is self-adjoint. T equal to t star. Okay. Proof again, it's same thing as polarization identity. What is the spelling? Polarization identity. So take bxy equal to inner product txy. Okay. Then I want to write you have done it in the assignment, so I believe that, and I use the polarization identity. Okay. Then it depends on what is the sesquilinear form you are taking. Polarization identity is true for any sesquilinear form, and you can take the sesquilinear form as the inner product, but I am taking the sesquilinear form with txy. Okay, that's also a sesquilinear form. So I am taking that. So 4 times txy equal to summation I power k equal to 0 to 3 t of x plus I power ky, okay, x plus I power ky. That's what I get. If I apply to this is uniform, not for the inner problem. If I apply to this, I get this. Okay. Now I want to verify that this is same as, it's enough to prove that what I want, txy, whatever are 4 times txy equal to 4 times x ty. That's what I want, which is equal to 4 times ty x bar. That's what I want to get, right? But then we have assumed that txx is real. Okay, so it's enough to prove whatever that sum we have, k equal to 0 to 3 I power k tx plus I power ky x plus I power ky. What do I get? Not enough to prove. I just compute that. Okay, that is equal to, this is what the first line is, txy, 4 times txy is this. Okay, now I write it in the following: k equal to 0 to 3. I keep the I power k here. I can multiply this by I power minus k. Okay, what is I power minus k? If I power k equal to I power minus k will be minus of that, no? Yeah. I can multiply by I power minus k on both sides. So this becomes I power, no, I can multiply by I power k itself. Okay, what will happen if I multiply by I power k? That will become no. What I want to say is, if it is 1, then I keep it like this. If it is minus 1, then I multiply this by the t part by minus 1. Okay, I'm just saying this is true. Okay, there is a t here. Okay, this ty. Will I get a minus sign somewhere? I power k dx plus 1. What I have done multiplied by I power k. Okay, I think this is true. If you just verify it for each one of them, I mean 1 minus 1, I minus I. If you just verify that, this will be true. Okay, I don't want to do that. I think hope you can verify. This is equal to I power k t y plus I power kx plus t of y plus I power ky. But then you can put a bar here because this is real is what we have assumed. Okay, you can put a bar here and you get that the whole thing is equal to 4 t y x bar. Okay. I mean, this you have to verify. I'm sure it is true. Okay. So please just verify this. This is true. So we have proved that if txx is real, then t is self-adjoint. So that's what I have used here. Yx is self-adjoint, then yx is real, then yx equal to yx star equal to x. So this proposition is true. I mean, you can ask any question. I can go through the whole thing again, what I have done. This is anyway very easy, and it is in the book directly. It's there. Not all verifications are there, but it's more or less there. Okay, so let me move to the next topic. It's fine. If you don't object, I will go. I will go move to the next topic. Okay. Okay. What is the next topic? Next is about approximate eigenvalue. So I have defined what is an approximate eigenvalue. Then I want to define a proposal, prove a proposition. Okay, definition. See, the point is In finite dimensional, something is in the spectrum means it's an eigenvalue. Here it may not be the case. Here we will prove that something is in the spectrum, then there is an if it is normal, then there is an then there is an approximate eigenvalue for that. Okay. So a lambda in C is an approximate eigenvalue. Value for T will be of H if there exists Xn with norm Xn equal to 1 such that T minus lambda Xn goes to 0. Okay. So it is just this limit is there. This is just approximate eigenvalue. There does not exist an eigenvector. If we have an eigenvector, then we call it as eigenvalues. But instead, we have a sequence of vectors, unit vectors, which satisfies this equation. This is what is called approximate eigenvalue. Okay. Proposition T is normal, T or Z is normal. Normal, then 1. T is invertible. This does not involve approximate eigenvalue, but this is 2. Then T is bounded below. That is, there exists epsilon greater than 0 such that C, small c greater than 0. C greater than 0 such that norm of Tx is greater than C times norm x. Operator is bounded above means the inequality is reversed. Okay. Then the second part is T is something is in the spectrum if and only if it is an approximate eigenvalue. This is true for normal operators. Okay. Even for normal operator, it's not true that something is in the spectrum means it's an eigenvalue. It's true in finite dimension. Okay, here it's not true. Proof. First one. So this thing we have seen as a corollary to closed graph theorem, as a corollary to open mapping theorem. Okay. So if T is invertible, but we need that T of H is closed. Okay, we need we have seen it in the earlier class. I didn't do it. I think Lakshay did that. Open mapping. I don't know who did. Lakshay did that, I think. Okay, no, I did open mapping theorem. This is a corollary to that. I think he did that. So if you have range of T is closed, okay, range of T is closed, then T is bounded below, then it's a 1-1 onto map from the domain to the range. Okay, so to apply open mapping theorem, we need the range to be a Banach space. Okay, so here it will follow. If T is normal, it will follow. The range T is closed, it will follow. So that's what we will use here. Okay, so 1, T is invertible. We want to prove that T is bounded below. That is clear, but that we have used, that is proven in the last course also, but let's just do it. So norm X is equal to norm T inverse Tx, which is less than or equal to norm T inverse times norm Tx. Okay? And this implies norm Tx is greater than or equal to 1 by norm T inverse. This is the C. Okay, so 1 implies T is invertible, then it's bounded. Okay, this way. Now this way T is bounded below. Assume. Then we want to prove that it is invertible. We want to use the fact that T is normal. Okay, so T is bounded below means what? It means there exists a small c greater than 0 such that norm Tx is greater than c times norm x for all x. then this is same as saying norm T star X. Okay? This is also true for T star X also. Notice that if T is invertible, T star is also invertible. It is just T star inverse is T inverse star. So can you just see that? You can use the inner product. Write that and you will get it. Okay, I will come to this after this. That's not used here. I'm just saying. So we only want to prove T is invertible from by assuming this. If T is bounded below, then T star is also bounded below because it's normal. Okay, normal Tx norm Tx equal to norm T star X. So this is also same as C times norm X. Okay? So this implies kernel of T is 0 because I mean if norm Tx equal to 0, then norm X equal to 0 by this inequality. So it's also true that kernel of T star is also 0. But then kernel of T star equal to range T closure. Kernel of T star per equal to range T closure. We have proved it, no? Have we proved it? Anyone remembers? In this class, in the two
Yeah,
class,
yeah, yeah.
we
You
proved
proved it.
Yeah, so it's direct. Okay, so this implies range T is dense because this is equal to 0. Okay, this implies range T is dense in H. So we want to prove that range T is actually closed. So claim range T is closed, but that is just clear. That is clear. If Txn goes to some y, okay, then we have Txn is bounded below. Txn is greater than or equal to C times norm Xn. Okay. Txn goes to Txn minus, what is it I want to say? Txn is Cauchy. Okay. Txn converges to this. This implies Txn is Cauchy. Then Txn minus Xn is linear, is greater than C times norm Xn minus Xn. Okay. So this implies Xn is Cauchy. Xn converges to X in H. Since H is Hilbert space, it's complete. Xn converges to X. So this implies Txn converges to Tx, but then it's already converges to Y. So this is Y. So this implies Y is in range. So this implies range T is closed. Okay, that's what I've used. Range T is closed. So I've assumed that I have taken elements Txn in the range T, and suppose if it converges to Y, then Y also looks like some Tx. So that means range T is closed. Okay. Okay. I would like to hear from others. Only one person is saying yes. Sayantan is saying. And I know Sayantan has already attended Kesav's course, I think. You have attended, no? You have already seen these things? Or?
Yeah, yeah. So I attended a course on Hilbert spaces and linear operators
Yeah, so more or less you
in
have seen
August.
this. Yeah. So you
So
more or less have
there
seen
he
this.
did
So
some
I would like
spectral
to hear
theory.
from others. Yes or something. Okay. Not I mean, you can also say, but others should also say whether it is clear or not. Okay. Okay. So I proved that range T is closed. Now we have proved that range T is dense. So this implies, so from here, from whatever I have done here, this implies range T equal to H. Okay. So T is 1, 1, which we have already proved. Kernel is 0, it's 1, 1, and on 2. So T is invertible. By open mapping theorem, inverse is continuous. T is invertible as algebraically invertible. Okay. Algebraically invertible. Then T inverse is in B of H. Okay. T is, the inverse is also bounded by open mapping theorem. So because of that, the following first part of the proposition is true. T is invertible is equivalent to saying T is bounded below. Okay. Now I want to prove if lambda is a, so I hope this is clear. Okay. Now I want to prove the main theorem, main thing we want to prove. Lambda is in the spectrum of T. T is normal. We are assuming T is normal. Lambda is in the spectrum of T if and only if lambda is an approximate eigenvalue. So lambda is in spectrum of T. Okay. That is equivalent to saying, that is same as saying T minus lambda is not invertible. Okay. This is equivalent to saying T minus lambda is not bounded below. Okay. This is equivalent to saying there exists, not bounded below means what? There exists Xn with norm Xn equal to 1 and T minus lambda Xn is less than 1 by n. So, right? You can choose Xn such that T minus lambda Xn is less than 1 by n. It's not bounded below. So you have a sequence such that T minus lambda Xn going to 0. That's what it means by it's not bounded below. You cannot have an epsilon where the T minus lambda x is great. T minus lambda x is greater than norm of, you don't have an epsilon, you don't have something like this. Is greater than an epsilon. See, I mean, epsilon times norm x you will get, bounded below means, but then that x is norm 1, so you don't get it. This is greater than or equal to this epsilon. This is what is bounded below with norm x equal to 1. So you don't have an epsilon like this means for each n you will get an xn such that for any epsilon, epsilon equal to 1 by n, you will get something smaller than that. Okay, that's what this means. So, but then when you have something like this, then it's not bounded below. So these two statements are same. Okay. So this is what an approximate eigenvalue means. This is equivalent to saying lambda is an approximate eigenvalue. Fine.
Yes, sir.
Okay. So the whole
Yes,
thing.
sir.
Okay. Whole thing is done. Okay. So yeah. Then so, okay. Next two things are very simple things. I will finish it quickly. 6. So proposition or corollary. I think this is corollary. X is self-adjoint. Then this implies, otherwise also true. We'll come back to that. Sigma x is contained in R. Okay. Proof. So x is self-adjoint. Lambda is in x is self-adjoint, and lambda is in sigma of x. Okay. Then we have the following. Then lambda is an approximate eigenvalue. So there exists xn such that x minus, sorry, what is it? X minus lambda xn goes to 0. Okay. X minus, I mean, you don't need norm anyway. If it goes to 0, actually that is going to 0. This implies x minus lambda xn, the inner product with xn. Okay, this is equal to, this is less than or equal to, sorry, less than or equal to norm x minus lambda xn, norm of this, norm xn is 1. Okay, so you don't need. Okay, so this goes to 0. So this goes to 0. But lambda xn xn is just lambda. So you have sum of two sequences. This sequence is nothing but xn xn and lambda xn xn. Now lambda xn xn is just lambda. So that is just lambda. So this implies that other thing. So these things implies that x xn xn converges to lambda. Okay, but since x is level, this is real. Because since x is self-adjoint, we already proved it. Something is self-adjoint if and only if xx, I mean this quadratic form xxx, this is real. We just proved some time back. Okay, so because of that, this is real. So all these things are, some real numbers are converging to real. So this implies lambda is real. Okay, so we have proved if lambda is in sigma of x, it's in the spectrum, then it is real. That's what it is. Okay. Okay. So the final thing is this. This will be used later, but this is just clear. T is normal. T equal to x plus iy. Xy self-adjoint. Okay. And lambda equal to alpha plus I beta is in sigma of t with alpha beta real. Okay. Then there exists xn such that x minus alpha xn with norm xn equal to 1. I mean, there exist approximate eigenvalues, approximate eigenvectors xn with approximate eigenvalue alpha for x and beta for y. That's what it means. This goes to 0. Norm of y minus beta xn. This goes to 0. This is just easy because proof. This is because t is normal, t minus lambda is also normal. Okay. When lambda, yeah, t is normal, t minus lambda is also, lambda is just a scalar. T minus lambda is also normal. It commutes with its conjugate. Okay. I mean, which is just bar of this. T star minus lambda bar. Okay. So now we know that this is t minus lambda x for anything. This is equal to x minus alpha x square plus y minus beta x. We have already seen this for normal operators. The Cartesian decomposition. I mean, it is computing the norm is like computing the modulus for the complex numbers. It is something like this, which we have proved because of the deformation. Okay, so this is done. That's all for today. If you have a question, you ask. So, any question? Okay, if you have question, you ask in the beginning of next class, and I will sort out that P before the next class.